Solving a Pulley Problem Using Conservation of Energy by Jared Koenigsberg and Justin Park. To install a new window, we need to get 19 kilograms of glass from the first floor of a building up to the second, but the stairs are blocked. The first floor is 4 meters high and the second is 8 meters above the ground. Luckily, there is a 6 kilogram pulley above the second floor and we have two 1 kilogram platforms. From the first floor window, we place our trusty 29 kilogram counterweight on one platform and place the glass on the other. To prevent disaster, we need to find the speed of the glass when it reaches the second floor. Our goal is to find the final speed of the glass when it reaches 8 meters high. And our diagram shows mass 1 of the glass at 20 kilograms, mass 2 of the counterweight at 30 kilograms, mass 3 of the pulley at 6 kilograms, both heights of mass 1 and 2 at 4 meters, and the final height at 8 meters. Initially, we have potential energy of mass 1 and mass 2, plus kinetic energy of mass 1 and mass 2, plus rotational kinetic energy of mass 3. However, both mass 1 and mass 2 and the pulley are all at rest, so we can cancel out the kinetic energy and the rotational kinetic energy to leave us with potential energy of mass 1 and mass 2. Our final energy is equal to final potential energy of mass 1 and mass 2, plus final kinetic energy of mass 1 and mass 2, plus final rotational kinetic energy of mass 3. However, mass 2 will have no potential energy since it's on the ground. And that leaves us with potential energy of mass 1 plus final kinetic energy of mass 1 and mass 2 plus final rotational kinetic energy of mass 3. Thanks to the law of conservation of energy, we know that initial energy will be equal to final energy. So our energy equation will be potential energy of mass 1 and mass 2 equal to final potential energy of mass 1 plus final kinetic energy of mass 1 and mass 2 plus final rotational kinetic energy of mass 3.
Using our knowledge of physics, we know that the initial energy of the system is equal to m1gh1 plus m2gh2, and the final energy of the system is equal to m1gh final plus 1/2 m1 v squared plus 1/2 m2 v squared plus 1/2 I omega squared. Since we know that I, the moment of inertia of the cylinder, is 1/2 mr squared and omega is v over r, we can simplify our equation to take out the radius, which does not affect the speed. Since we know that the displacement upwards of mass 1 will be equal to the displacement downwards of mass 2, we know that the initial height of mass 1 will not affect our problem. We can then further simplify our equation to get m2gh2 is equal to m1gh2 plus 1/2 m1 plus m2 v squared plus 1/4 m3 v squared. Further simplifying our problem, we get m2 minus m1 all times gh2 is equal to velocity squared times 1/2 m1 plus 1/2 m2 plus 1/4 of m3. We can then substitute our values in, so we have 30 kilograms minus 20 kilograms multiplied by 9.8 meters per second times 4 meters is equal to 1/2 times 20 kilograms plus 1/2 times 30 kilograms plus 1/4 times 6 kilograms, all times v squared. This gives us 392 is equal to 26.5 v squared. And then 14.79 is equal to v squared. And finally, v is equal to 3.85 meters per second. This is the final speed of the glass when it is at 8 meters.